Hello again to Physical Chemistry for Life Sciences. We are today starting Chapter 6, which is the rate of reaction, or what we call chemical kinetics. I am Ismail Badran, again, your instructor. So in this chapter, we're going to talk about the reaction rate and the rate laws. We're going to talk also about the rate constant and the difference between the rate constant and equilibrium constant. We're going to talk about two types of rates, which is the differential rate laws and integrated rate laws. And we'll finish up with talking about the Arrhenius equation and the temperature dependence. So why do we study chemical kinetics and why this chapter is important and what does reaction kinetics mean? First of all, I will give you here two examples of two reactions that actually I will show you that there is no relationship between the thermodynamics and the kinetics of the reaction. Let's consider first rusting of iron. So iron solid reacts with oxygen, as you know, and to form Fe2O3, which is the iron rust, the iron oxide that you see in the pipelines, and this is actually posing a big problem for the state of Qatar, especially because the oil pipelines and the natural gas pipelines, they rust all the time. Now this reaction, for example, has a delta H of minus 1184 kilojoule per mole, which this reaction is very exothermic. There is also entropy value of 146.4, so the entropy increases across this reaction in the course of this reaction. And if you do the math, you will find delta G to be equal minus 1015, and this means this reaction is spontaneous at room temperature, and it's exothermic. So you expect this reaction, because it's exothermic and spontaneous, if it comes to your mind that this reaction should happen by itself very quickly. But the fact of the matter is, this reaction is very slow. This is an example of an exothermic reaction. It is spontaneous at room temperature, but it's very slow. So the first lesson here is you don't relate the idea of exothermic and endothermic to the rate of the reaction or to how fast it goes or to the speed of it. Exothermic does not mean fast, and spontaneous does not mean slow or fast. There is no relationship between the two. I will give you another example here for an endothermic reaction, but it's fast. This is the beautiful natural phenomena of photosynthesis, where plants takes CO2 from the air and water from the ground to form oxygen, which we breathe, and the glucose that goes to the fruits and to the seeds that we can eat and enjoy. Now let's take a look at the thermodynamics of this reaction. This reaction is very endothermic. That's why the plant takes the heat or the light from the sun for the reaction to go on. It's very endothermic. It's 2800 kilojoule per mole. But this reaction is spontaneous. Delta G for this reaction is actually negative. That means the reaction, it takes place by itself. Okay, so it is an endothermic, but it's spontaneous and it's fast. So I gave you two examples of reactions, and the examples can go on, of course, for several endothermic or exothermic, and they are spontaneous, but their speed has nothing to do with the thermodynamics. So here is a new chapter in your course. Okay, it's called chemical kinetics, and we're going to talk about a few concepts here, and please do not mix these concepts with what you learned before. Delta G has nothing to do with the rate of the reaction, and delta H has nothing to do with the rate of the reaction. Now, as I said, I'm framing this here in a green box. There is no direct relationship between the spontaneity of a chemical reaction and how fast they can go. So if you take a look at this potential energy diagram for a chemical reaction, you start with reactants, which is in the you start here with some reactants, and the reactants, they can go to products through this red curve here. The difference in energy between the reactants and products, as we learned, is called delta H for the reaction. So this difference here between the reactants level and the products level, this one is the delta H, and you can tell this is an endothermic reaction because the products have higher energy than the reactants. Now, This delta H here can tell you if the reaction is exothermic or endothermic. In other terms, if delta H is negative or positive. Now here, the energy difference between the reactants and the top of this curve, we call it activation energy, and we're going to define this in this chapter. This activation energy determines the speed of the reaction. If this activation energy is high, then the reaction is slow. If this activation energy, as it goes lower, the reaction becomes faster. But the activation energy EA has nothing to do with delta H. And if you change delta H, the activation energy will stay the same. You can add a catalyst to this reaction. The activation energy might decrease, but this has nothing to do with delta H, and delta H won't be affected. And in summary, there is no direct relationship between the thermodynamics and the kinetics of the reaction. Now, let us now introduce some basic concepts into chemical kinetics in order to study this. So first of all, we define the rate of the reaction, which is basically the speed of the reaction. So if you have a car that going on a highway, the car will have a speed is equal distance over time, or delta x over delta t, as you learned in physics. Now the rate of the reaction, so the basic data of the chemical reactions are the concentration of the reactants and products at different times after the reaction has been initiated. So we just replace here the speed, instead of saying the speed is equal distance over time, we say that speed is equal concentration over time. Okay, so if a chemical reaction that goes on, it's not the distance that the reaction goes on, it's not change in concentration. So that's the definition of the rate of the reaction. The rate is equal change in concentration divided by changes in time. So this rate of the reaction depends on four things actually. First, it depends on the reactant concentrations. Okay, the initial react. So how much you're putting in the reactant concentrations. It's also affected by temperature, okay? And usually the higher temperature, the higher rate of the reaction. So if you want to speed things up, you always heat them up. It depends very much on the physical states and the surface areas of reactants, and that's why we are now interested in the beautiful science of nanotechnology and nanoparticles, because nanoparticles, they have higher surface areas and they speed up reaction rates. It also depends on the solvents and the catalyst properties if they are present. Now, if you start with some reaction, let's say a very easy example, which is A goes to product. So you have one reactant that goes to product. As the reaction goes on, as time goes on, the concentration of the reactants will decrease, of course. It's not going to decrease linearly, but it's going to decrease and exponentially as this curve shows here. So the concentration will change over time as the curve shows. It will start at some value and it decreases. Now this is a concentration versus time graph, and as you learned from the previous chapters, if you take the derivative of this graph at any point, the derivative would be the slope of the line or the tangent of the line at any point, and that would be the delta concentration divided by delta time, and this is exactly what the reaction rate means. So the rate of the reaction is actually delta J over delta T, where J is the concentration. That's the way to call delta J. Now you can calculate the rate at any point. You can calculate it at this point at the beginning here. I hope that you see my pointer. Or you can take it at the middle or at the end. At any point across this curve, you can determine the average rate. And you can tell here that the rates of the reaction are not the same. If you take it at the beginning, the tangent will be different than taking it at the middle or at the end. And therefore, the rate itself, it changes. Okay? Now we define another thing, which is called instantaneous rate. The instantaneous rate of the reaction is the slope of the graph of its smaller concentration plotted against of time at an instant of interest. That means at any time. That's what we call instantaneous rate. So the instantaneous rate is it might have different values. You can calculate the instantaneous rates here or here or here or here. Now you can tabulate these and take the average, and that will be the average rate. Okay. But the most important one of the whole rates is the initial rate, is the one that you calculate at the very beginning of the reaction. This is the one we are using actually in this chapter. So to summarize here, we have three different types of rates. We have the instantaneous rate, which the one you calculate at a given point, let's say at the beginning, at the middle, at the end, okay? At time 0, at time 10 seconds, 20 seconds, 1 minute, whatever. This will give you the instantaneous rate, and the instantaneous rate will be different, of course, between each point. You have also the average rate, which means the average of the whole thing, okay? And you have also the initial rate, which is the one they taken at the very beginning of the reaction, and this is the most important and the most used. Now, this graph here, it's again molar concentration versus time for reactants. So the reactants is the one, it's just a copy from the previous one. But here I'm plotting the concentration of products on the same graph. The reactants goes down, of course, because they decrease with time. The products will form. That means their concentration will start from 0 and it will increase. You can actually calculate the rate of the products as well for the reactants. But the difference between the two is that for the reactants, we use the word rate of consumption. That means the reactants are being consumed. And therefore, the rate is actually negative because if you see here, this line is going down. So the slope of this line here will be negative. So the rate of consumption of the reactants is equal minus d, let's say A over dt. Okay? Where the rate of formation of products is plus مثلا dd over dt. Okay? So that's for products we always use plus, and for the reactants we use minus. Some technical difficulties here. Okay, I got my students watching, so that's good. Sorry, I am facing some technical difficulties, so I'm gonna start this again. While I'm solving this issue, does anybody have a question so far on the rate? No? Okay. Okay, so we are back now. Now, let's consider a reaction that is A plus 2B Let's consider a reaction that is A plus 2B goes to 3C plus D. Now, clearly here, the rate that where A is disappearing or consuming is different than the rate of disappearing of B because the molar ratios are different. And also it's different than C. A and D might be similar. So in this one, we can define that the rate of the formation of D is equal at 1/3 of that of the C. It's equal minus dA over dt, and it's equal 1/2 dB over dt. So these ratios here, you can take them right away from the coefficients of the reaction. Making sure to put plus for the products and minus for the reactants. And generally speaking, the rate of the reaction is equal 1/V d zeta over dt. This is the most important equation here that you need to apply for your reactions. So where V is called the rate of the reaction. It's the rate where everybody is going on in the same speed, okay? That's the rate of the reaction. 1/V is 1 over the coefficient. Large V here, capital V is the coefficient. d zeta over dt is the change, it's the rate or the rate for the individual species. And I'm gonna explain this here in this question. So let's take an example that 2NO2 gas goes to 2NO gas plus O2 gas. So clearly in this figure, you see here that the nitrogen dioxide, NO2, it's the green line, it's decreasing, okay, and it has a rate. You can calculate actually that rate at a given point by taking the slope, okay, you take delta y over delta x, you divide this by this, and you can find the rate, and you make it minus. And the rate of NO2 should equal to the rate of formation of NO, because they are 2 to 2 here. They're having the same molar ratios. But oxygen, which is the red line, it's forming at a rate that is slower than these rates because it has a different molar ratios. It has 1, so it's going to be half. So in this case, we can say that the rate of concentration of NO2 decreases with time, and the rate is a negative quantity, and therefore we say the rate of NO2 is minus delta NO2 over delta T. And for NO, it's equal to plus NO over delta T. But for oxygen, it's going to be half of that value, because oxygen will have a lower value. To practice this, let's solve this question and try to understand the difference rate. It says consider the reaction 4pH3 gas goes to P4 gas plus 6H2 gas. In a certain experiment over a specific time period, 0.048 moles of pH3 is consumed in a 2-liter container each second of the reaction. What are the rate of production of P4 and H2 in this experiment? So let me do that step by step for you here. Okay. So 4pH3 gas goes to P4 gas plus oxygen plus 6H2. No, sorry, not H2. For all gases. Now it says that each second there is 0.0408 of pH3, so this is 0.0048 mole are disappearing each second in a 2-liter container. So this is happening in a 2-liter container, okay? Calculate the rates of production of P4 and H2. So we need the rate here and the rate here. Well, that's a very easy question, because first you calculate the concentration of pH3, which is equal 0.048048 mole divided by the volume, which is 2 liters, and you will have the answer to be 0.0024 molar. So I just it's easy if this is 1 liter, but because the volume is 2 liters, then we just find the concentration to be half of that number. Then the rate of pH3 is equal delta J, or delta concentration, over delta time. He says it's changing by this value every second. That means this is the change, so it's 0.024 molar or mole per liter divided by 1 second, because he said, so you get the same answer, which is 0.024 molar per second. So this is the units of rate. Now let's talk about the difference rate. The most important thing that you need to learn from this question here is that this equation, which is I showed you in the previous slide, is that the rate is equal 1 over V d zeta over dt. And this means that in this question, the rate of the reaction should equal, now it's 1 over V, so it's 1 over 4 rate of pH3 minus, because it's disappearing, and this should equal to plus 1 over 1, so this is V rate of P4, and this is equal to 1 over 6 rate yani V of H2. This is plus. And this means that H2 is actually going at 6 speeds of P4, okay, and P4 and the PH3 is 4 times P4, and so on. Now, the easiest way to solve this question is first to find the rate of the reaction. The easiest way to solve this question is first to find the rate of the reaction. If you find the rate of the reaction, which is this one, you can calculate whatever you like. So let's find the rate of reaction. Now the formula here is that the rate of the reaction is equal 1 over 4 the rate of pH3, صح? Now the rate of pH3, we found it to be 0.020246. We found it to be 0.024 seconds. So therefore, rate of reaction, which is V for the reaction, is equal to 1 over 4 times this number, which is 0.0024 molar per second. And this will give you يعني ربع هاي الكمية 0.0060630 molar per second. This is the rate of the reaction. From the rate, you can calculate whatever you like. You can calculate this one, and you can calculate this one. In this case, because P4 has a coefficient of 1, this is the only one that is actually going on a speed that is equal to the rate of reaction. So V of reaction is equal 1 over 1 V of P4. يعني ال P4 بتساوي نفس الفاليو 0.0006 molar per second. But the hydrogen will be different. Hydrogen will be 1 over 6. So V of reaction is equal to 1 over 6 V of H2. يعني ال V of H2 لازم تساوي 6 times 0.006 molar per second. And this equal to 0.0036 molar per second. So these are the answers.
Doctor, they are negative, right? Or not?
Just 1 second, please. So let me summarize here. Look back at the question here. So in this case, the rate of the reaction will be 0.00036. This is the rate of the reaction. This guy, because it has 1, it will have the same rate. This one will be 6 times of this rate, and this will be 4 times of this rate. شفتوا كيف؟ يعني بكون ال B4 ماشي على نفس السرعة، ال H2 بكون بتكون 6 أضعاف هاي الكمية، وال PH3 4 أضعاف هاي الكمية. This is simply this question. Yes, my friend, go ahead. What is the question? What's your question?
I was saying if they are negative or not, because we have a negative sign.
Yeah, so
with the PH3.
here this is positive for the H2. For the P4 it's positive, and for the PH3 it's negative. I could make it negative here. This is negative here. Yes. So based on this.
دكتور.
نعم.
يعني الريت اوف رياكشن دائما بده يكون بوزيتيف.
ريت اوف رياكشن دائما بوزيتيف صحيح. وكله بيعتمد عليه، كله بيعتمد عليه. خلينا نحل سؤال آخر. هو الموضوع مش عليكم، مش أنا جديد عليكم. Let us just practice this question and we'll go back for discussion. Just to the idea gets in your head, okay? Let's say that consider the reaction 4NH3 plus 7O2 goes to 4NO2 plus 6H2O. This reaction has 4 different coefficients, okay? At a certain instant, the initial rate of disappearance of oxygen gas is X. Let's consider that the disappearance of oxygen is X. What is the value of the appearance of water at the same instant? بنفس اللحظة. الأكسجين X معناته الواتر كم بتكون؟ Is it 1.2x? Is it 1.1x? Is it 0.86x? 0.5x? Or cannot be determined from the data? I will give you 1 minute to think about it and come up with an answer, please. A, B, C, or D, or E. You can also use the chat window to give you an answer. Anybody else want to share the answer? Kawthar, can you please open the mic and tell everybody how did you get C?
I simply divided the 6 divided by 7, so I get 0.857, which is
And how did you do that?
0.86.
I'm sorry, why did you do that? Why did you do that?
Because I divided the number of coefficient of the products above products over reactants.
So you're saying that H2O will be formed in a rate that is equal 6 over 7 of O2. That's what you're saying?
Yeah.
And that's exactly the answer. Yes, thank you, Kawthar, so much. This is exactly what happens here, is that H2O is forming in a ratio equals to its coefficient divided by the 7O2. يعني Kawthar, in other ways, she made شو بسموه هذا نسبة وتناسب, proportion. She said if X is forming at X, then 7O2 will give you 6H2O. X is how much? And she did the cross multiplication. This works too. This works too. So this is Kawthar what she did. I will solve this question in 2 ways, okay? I will solve it Kawthar way, and then I will solve it using the rate of the reaction. So here it says 4NH3 plus 7O2 goes to 4NO2 plus 6H2O. The question says this is X. This is how much? Kawthar said that the rate of H2O should equal to 6 over 7 of O2. صح يا Kawthar? Which is 0.8. If you divide 6 by 7, it will be 668X, which is answer C, which is the correct answer. But you can do this different way. Let us call this answer A, okay? Now you can do it in B, where you find actually the rate of the reaction, the way I was solving it before, and this is the safest way. The rate of reaction is 1 over 7 of the V of the reaction of O2. This is the one we know, okay? Because we know that the rate of the reaction is equal 1 over V D, let's say O2 over dt. This is the general formula, okay? Now, then the rate of the reaction in this case is equal 1 over 7. The rate of O2 is X. Then it is 1 over 7X. Then you bring this one and you plug it into the water. Then then you say the rate of the reaction is equal. I'm just gonna up to the plus or minus soon. It's 1 over 6 of the rate of H2O. يعني الريت بيكون H2O بيكون ماشي 6 أضعاف. ليش؟ Because here the V of H2O, if you do the cross multiplication, it will be 6 times the rate of the reaction. And therefore, it's equal 6 times 1 over 7x. And that should give you the same answer as we did before. To solve the problem of X plus and minus, here you can say that the rate of reaction is minus rate of O2 is minus, then 1 over 7. You can put here minus, so the rate of reaction is minus, if you like minus 1 over 7 minus small, and this will be plus. V reaction, this is plus, and this is plus. يعني just put minus and plus where whatever it says for products or reactants. Okay, so I hope that you get this point and you can practice at home similar questions. Okay. Now, guys, let's move on to something that is really important, which is the rate law. The rate of reaction is often found to be proportional to the molar concentration of reactants raised to a simpler power. So, for example, it may be found that the rate of is directly proportional to the concentration of reactants A and B. So, the rate of the reaction is equal to a rate constant equals Kr times A to the power m times B to the power n. This is how we formulate a rate law. It was found experimentally that when you put some reactants together like A and B and C, generally speaking, the rate will depend on their concentrations, power to some power, m and n we call them. These are the powers. M and n might be 1, 1.2, 3, 4, whatever numbers. And we have here a constant, which is the rate constant is equal to Kr. That's how we define the rates, the rate of the reaction. This is called, the box in green here is called a rate law. A rate law is an equation that expresses the rate of reactions in terms of the molar concentrations or partial pressures of species in overall reactions, including possibly the products. This is how you define the rate law. You define it in terms of reactants, not products. And V is equal Kr times A power m phi B power n. Now let's take this equation and break it down so we can understand it a step at a time. First, it's the rate. It's the V. What is the rate? It's the rate of the reaction and has units always of units of concentration over units of time. So in the previous questions, let's go back to that question about P4. Remember that we found the rate of reaction. It was equal actually to 0.06 molar per second. Molar per second, that's a unit of rate. Or you can write it as mole dot liter minus 1 second minus 1. The rate of the reaction units does not change. Make sure that you write this down in your notes, that the units of the rate do not change. It's always units of concentration divided by units of time, or molar per second, or mole per liter per second. Now what is this Kr here? This is a new thing for us. Kr here is called the rate constant of the reaction. Now it has different units. This is nothing to do with equilibrium constant. That when the large K, that's why I was always telling you that there's something called capital K, which is the equilibrium constant, the one we studied in the previous chapter. And now we have the small k, the small capital K, and we call it a rate constant. Now this one has units, and its units they differ between it's a first order, second order. And this Kr has no relationship with the equilibrium constant K. I made this as a note here, that this small k, because I know that students, when they move on the course and they come close to the final exam, they start mixing things up. They start mixing the idea of the rate constant Kr with the equilibrium constant. They have no relationship between each other. Now, M and N are the rate, they call them the power, the orders of the reaction, the order of the reaction, okay? And these might be actually digits, like 1, 2, 3, 4, and they might be also fractions. Let's say like 1.5, or N is equal to 2.3. That's also possible. M and N also can be 0. And when you power things to 0, it's equal 1. It's like it's as if it does not exist. So the rate law of the reaction is determined experimentally and cannot in general be inferred from the stoichiometry of the balanced chemical equation of the reaction. So that's a very important rule in chemical kinetics, that the rate law, you write it down by going to the lab and do an experiment, and from the experiment results you can infer your rate law. You cannot actually just look at the equation and find the rate law. Okay, you can relate relative rates to each other by looking at the coefficients as the previous examples, but for the rate law itself, you cannot actually write it down from the coefficients. So an example is, let's take this example. 1H2 plus 1Br2 goes to 2HBr gas. You can think that the reaction rate is equal Kr times H2 times Br2, but it's not. this question, for example, has a very complicated rate law. It's V equals, you see here, there is 1.5 and so on. So you cannot actually write the rate law by just looking at the equation and do that. So here, people think by looking at this equation, you can think that the rate law, so rate is equal KR times the first, which is reactant, which is H2 power 1 times BR2 power 1. This is wrong because you cannot do this. Like you have to go to the lab, you do an experiment, and you obtain some data, you analyze it. It's a very long process, and you find the rate law. And actually, the people who did this before, they found the rate law to be in this form. Okay, it's very complicated rate law. So, for example, I was given a question to my students in the old days that says, consider the reaction 4NH3. This is the same reaction that we've been discussing a minute ago. 4NH3 plus 7O2 goes to 4NO2 plus 6O H2O. And he says the rate law for this reaction is A, B, C, D, or E. I will give you a minute. You can put your answer in the chat window if you like. Only Rana and Kawthar are answering. And Helen. Amara, Duha, very good. Now, can someone please open the mic if you don't mind? Not Kawthar or Rana, and tell me why you think the answer is E. Like, can you go over the answers and tell me what's going on? Any volunteers? No volunteers?
He is not the me, I'm the volunteer.
Sorry, speak your name and talk to me, please.
Hala.
Yes, Hala, تفضل.
We can determine the powers from only experimentally. We can determine it because of the equivalence equation only experimentally, right?
That's right. True, Hala. The answer is E. This is one of the rare questions that comes in the exam, and it says none of the above, صح? So yeah, the answer is none of the above in this case. The answer is E, because the rate in A, it says V is equal KR times NH3 power 4 times O2 power. Well, who told you this? Maybe it is, maybe not. Maybe the reaction, sometimes the rate law agrees with the coefficient, sometimes it's not. And there is nothing in the question that tells us this is the correct rate law. In number B, somebody write down the rate of reaction is equal NO2 power 4 times H2 power 6. First, he forget to put the rate constant. Second, he is writing the rate of reaction in terms of product. Thirdly, he put the powers from the coefficients. Everything possible is wrong in this answer, in B. In number C, somebody is writing the rate law as if she is doing the equilibrium constant. You see, it's products divided by reactants, and she spent some good time doing this, putting all the coefficients together. But again, this is wrong because first, the rate law has nothing to do with the equilibrium constant. Secondly, you cannot know what the rate law until you have some experimental data. And thirdly, D is also wrong. Okay, so the answer for this question is E. Now, how you determine the rate law? We're going to talk about two ways to do that. Inshallah, soon, the isolation method and something we call the initial rate method. But first, let's talk about the rate constant, because this is a very important concept in chemical kinetics. The rate constant KR. I actually love. Oh, did I write this in capital? Guys, is this a typo? Is this capital or small? This should be. Oh, okay, sorry. So I will correct this typo. This is KR, okay, like that. I saved my file. You can actually change it in your PowerPoint yourself. Khalas, I will rely on you to change it into your PowerPoint. It's KR, small. Type. What is the rate constant? V is equal KR A orbit, A times B power M and N. So AR is called the rate constant. This rate constant is characteristic of the reaction being started is called the rate constant. The rate is independent of the concentration of the species taking part in the reaction, and it also depends on the temperature. So it's a constant similar to the equilibrium constant, is that it does not change by changing the concentrations. It's a constant. So whatever you do with the experiment, you can increase A, you can increase B, you can start with different concentrations, but the rate constant Kr will stay as constant as long as the temperature is constant. The only thing that affects the rate constant is actually the temperature. If you increase the temperature, usually you increase the rate constant. But at a constant temperature, at let's say room temperature, Kr should be the same. Now, what are the units of the rate constant? That's a good question. Does it have a unit? Does it have units? Yes, it has a unit, but its units, it differs between the reaction and not. Because the units of Kr are always such to convert the product of concentrations into a rate expressed as a change in concentrations divided by time. يعني بمعنى آخر, the rate constant should have units, this rate constant, okay, should have some units, where F, this is in molar per second, right? That means this whole term should be molar per second. This is the ideal. The rate constant should have units, some units, I don't know what they are. That this whole term to the right, KRAB, should equal to molar per second. So you can actually do that yourself. You can derive the units of the rate constant. So for example, given the reaction M plus 2M goes to G plus 2H, just a hypothetical reaction. Somebody found the rate law to be equal, V is equal Kr times M, okay, times M power 1, as if N does not exist, or as if its N is equal N power 0. So the V is equal Kr M power 1 times N power 0. This is 0 order for N. N does not exist. The question says, what are the units of Kr? Well, that's very easy, because the rate is equal Kr times M, right? Is it not? So yes. He says, what are the units of Kr? Well, I know the units of V, the rate is always molar per second, that does not change. This equal to Kr. Now what are the units of concentration? It's molar, isn't it? Then this goes with this. Then the Kr should have units of 1 over second, or second minus 1. And this is the unit of first order reaction. This is, we just know now, we just derived the first units of first order. So first order reaction always have a rate constant with units of second minus 1. This is, once you see second minus 1, you know it's always first order reaction. And I will leave you to do this as a homework. A reaction has a rate law of kada. What are the kada? You can do this at home, please. It's easy, similar. But now, let's talk about the reaction order. So far we've been talking about three things: reaction rate. Now we know what is reaction rate and how to write the reaction rate order, the rate formula, and what is units and so on. We also talked about the Kr, which is the rate constant. Remember, I was referring to this slide. So now we know what is V, what is the rate. We talked about the Kr, how to find units. Now let's talk about this M and N, which are the orders of the reaction. The orders of the reaction, the order can be first order, that means 1, second order, 2, or third order, or fourth order, or whatever. Now the simplest one is the first order. We say V is equal Kr times A, where A power 1, and it's because it's A power 1, that means it's first order in A. In the second example here, and of course, I just want to mention that this chapter, the reaction kinetics and reaction rates, is the most important chapter in this course because of two reasons. The first reason is that you guys are pharmacy, so your pharmacokinetics and your pharmacology and your whole pharmacy future will depend on the understanding to the basic concepts of this course. You will spend a lot of time in your life doing pharmacology and pharmacokinetics. And the second reason is that the project of this course, which worth I think 20 marks, 10 marks, is based on this chapter. So once we finish this chapter, I will give you the project to do your project. So let's go back. First order in A means A power 1. This could be also A power 1, B power 1. So we say this is first order in A, first order in B, so it's totally second order. Or we can say V is equal KR times A square, which is second order in A. So I can give you one more example here. Let's say rate is equal KR مثلا times A power مثلا 2 في B power 3 مثلا. So in this case we say this is second order in A, third order in B. Second order in A, third order in B. Total order is 5. This is fifth order in total. So this is how you determine the order. I just want to mention that the order actually does not have to be an integral order. يعني it doesn't have to be 1, 2, 3, 4. You might have a fraction order like 0.5 or 0.3, and this one, and many gas reactions do actually. يعني they do have non-integral orders. And some reactions, they have zero order reactions. That means the V is equal KR times A power 0, which means the V is equal actually KR only. And this is the case in many enzymes. Now, how you determine the rate order and how do you determine this? We can use two methods, which is the isolation method or the method of initial rate. Let's take a break for 1 minute here, take attendance, and then we go back inshallah. And if you have any questions, you can ask me. Can everybody please log into her Blackboard and attend the course for me, please? And the code is the code is 8086. Anybody has a question? 8086 is the code, please. Layla, which question? Can you open the mic? Tell me which question. Unfortunately, I don't have time to repeat it. Maybe after the class, if you have any time, I can solve it again for you. But unfortunately, I'm out of time. If you're talking about this question, the PH3, I am out of time here. But simply you can do the proportion thing, or you can calculate the rate of the reaction itself, and then from that you can calculate everything else based on this formula. Yes, thank you. Anybody else has a quick question? No? Yes? Did you guys attend the course? 8086 again, last call, please. 8086 is the code. So if doctor saying that we cannot determine the rate law just by the coefficients, so how in the world we're gonna determine the rate law? Well, I said we can do that experimentally, or you can actually study computational chemistry like me, and you do calculations in the computer, and you obtain the rate mechanism and rate laws, and that's what many people do. But the first method in determining the rate law is called the isolation method. So in the isolation method, we propose that the V is equal KR times A times B, and then we use one of the reactants in excess. That means we use a large excess of the reactants. Let's say we use 1 mole of A but 100 moles of B. In this case, the concentration of all reactants are constant except 1. And in this, for if B is in large excess, it's a very good approximation to take it as a constant. And if B is too much, if you're using too much of B, then we consider its change in concentration is constant. That means it's not changing over time. Then, well, in this case, we'll have two constants in this equation. We have the Kr, which is constant anyway, and the B is constant. So we combine these two constants in one constant. We call it Kr prime. So again, if we the isolation method is a trick. Okay, we're gonna trick the reaction. هي خدعة. What do? We use excess of B. We use مثلا 1 mole of A and مثلا 50 moles of B. If we have 50 moles of B, there is no change in B. What's gonna be the change? A small change. So we can assume then in this case that the concentration of B is constant. Then therefore, we'll have two constants in this equation, the Kr and B. Then we combine them into one constant, we call it Kr prime. And then the equation becomes V is equal Kr prime times A, where Kr prime هاي الجديدة اللي هي نفسها Kr في B. This is called pseudo first order reaction. This is spelled as pseudo, not pseudo. Some teachers or some instructors, they say pseudo. The P here is silent. This is called pseudo first order reaction. Pseudo in English means semi, وكأنه بالعربي. وكأنه pseudo كأنه هيك معناته بالعربي. Or it's like first order. كأنه first order, okay? هو مش first order حقيقة. It's not an actual first order. It's a pseudo first order. And the Kr prime is called the effective rate constant. This is a very widely used method in the lab to determine rate law by using a trick, okay, or by deceiving the reaction. We are actually deceiving the reaction by using an excess method.